Please.
All right. Well, thank you, first of all, to the organizers for the invitation to speak. So I'll be talking about some work that appeared on the archive last night with Hofi Hannes-Doder, one of our postdocs in Edinburgh, Luke Lipstrew, and my PhD student, Maria Polakova. Apologies. And it's a work in which we introduce a new method for working out the implications of the hierarchical principle, which is an idea that has its roots in the 60s and which places strong constraints on the discontinuity structure of individual Feynman integrals. So to motivate why we might be interested in understanding these types of constraints, we need to go back no further than our talks from yesterday, where we were reminded that Feynman integrals are very useful computational tools for carrying out the types of predictions in particle physics that we want to make, for instance, for LHC physics. But they quickly become very hard to evaluate analytically. So for instance, we heard about ongoing work to evaluate two-loop amplitudes involving just 5 particles and 2 external masses. And due to the difficulty of these calculations, it becomes reasonable to ask whether we can prove things about these types of integrals from first principles. So the type of analysis I'm going to be talking about today can broadly be described as Landau analysis, which is basically the study of where Feynman integrals become singular. So let me begin by introducing the types of integrals we'll be talking about. So I associate a Feynman integral I sub g with any graph or Feynman diagram G, where the type of integral we're talking about just takes the form of this product of propagators in the denominator, each of which is associated with one of the internal edges of my graph, where each propagator depends on the momentum q flowing to that edge and the mass we've assigned to it. So if we want to understand where these types of integrals become singular, our starting point is going to be the Landau equations, which were written down over 60 years ago and which describe a necessary set of conditions for such singularities to arise. And the picture we should have in mind when we think about the Landau equations is the following. The picture shown here, where I've depicted the space of integration variables, the loop momenta, where we're integrating over some contour gamma, and we have some singular surfaces in this space associated with where the propagators vanish. So these are some on-shell surfaces. And as we vary the external kinematic variables in our process, what's going to happen is these singular on-shell surfaces are going to start moving around in this space of loop momenta. And one thing that can happen, surfaces can pass through the original contour. This is fine though, because we can analytically continue our integration contour out of the way. Another thing that can happen though, which is described by the solutions to the Landau equations. So it describes configurations in which multiple of these singular surfaces can approach this contour from multiple directions in such a way that the contour gets pinched and we can't deform our contour out of the way. And in this way, the integral itself inherits the singularity of the integrand. So today, though, I'm going to be focusing on a slightly more refined version of this question, which is what happens after we start computing discontinuities. So instead of just the Feynman integral I, I'm going to be considering the discontinuity of a Feynman integral with respect to some kinematic singularity lambda. So this can be, for instance, one of the thresholds in our diagram. And the 0th order question we can ask is whether or not all the singularities that could arise in our original Feynman diagram or Feynman integral can still arise after we computed this discontinuity. So the answer to this question also goes back to the 60s and is definitely not. So we can already see this in simple examples, looking at Kutkovsky's formula, which tells us that if we want to compute a discontinuity with respect to some singularity in which a set of propagators have pinched the integration contour, what we should do is we should take our integral and we should replace those propagators that were involved in the pinch with these delta functions in the numerator. So if we have a singularity in our original Feynman integral, that in order to access it, we need to take one of these propagators off shell, we'll no longer be able to see that singularity in this discontinuity because we'll just be off the support of these delta functions. So a more general version of this statement is provided by the hierarchical principle, which states that once we put propagators on shell, when we compute discontinuities, we can never take these propagators back off shell. So this could be shown using Picard-Lefschetz theory, which essentially describes how the discontinuities of these integrals can be written as integrals where the integration contour has been localized to the pinched surface. So for instance, we end up with just these contours that are small little balls around the on-shell singular surfaces that pinch the contour in the first place. And so what we should really have in mind when we think about the discontinuities of Feynman integrals is a modified set of Landau equations where we've distinguished between the propagators that have already been involved in pinching the contour and propagators that have not been, because the propagators that have not yet been involved in some pinch can still be off-shell if we set the alpha parameter multiplying the on-shell condition in these Landau equations to 0. So the upshot is that we should be able to derive restrictions of the form shown here on the double discontinuities of Feynman integrals by comparing the solution of these modified equations to the original Landau equations. In practice, however, doing this is extremely subtle, and that's just because we're still not all that good at making sure we found all solutions to the Landau equations. In particular, we want to know for this purpose not just the kinematic locations of these singularities, but where they arise in Feynman parameter space or in loop momentum space. So for this reason, these types of constraints have only been worked out in a handful of examples. So for instance, at 1 loop and then at 2 loop for the sunrise and the ice cream cone integral. However, what I'm going to tell you about in the remainder of this talk is that actually these difficulties could be sidestepped for a very large class of hierarchical constraints. And the result is going to be a practical method for deriving discontinuity restrictions on our Feynman integrals of this form, where these dots indicate that I'm allowed to take any sequence of discontinuities before these discontinuities with respect to lambda and lambda prime. So these restrictions will be tailored to individual Feynman integrals, and we will not need to explicitly work out any algebraic lobes to find any kind of hidden solutions to the Landau equations that represent singularities in our Feynman integrals. And it'll be possible to apply this method to integrals involving any configuration of massive or massless particles, and the resulting constraints will hold to all orders in dimensional regularization. So let me begin, though, by making clear our intellectual debts. So the method I'll be describing builds heavily on 2 recent advances in the Landau analysis literature. One is an improved understanding of how cuts and discontinuities work in Feynman parameter space, and the other is a new understanding of how certain topological methods can be used to probe the singularity structure of Feynman integrals, along with an implementation of some of these ideas in the principal Landau determinant code by these authors. So the first move I'm going to make is I'm going to move to Feynman parameter space, which means I'm going to introduce Feynman parameters, integrate out the loop momenta in my integral. So that's going to leave me with an integral of this form, where I just have the u and f polynomials, which are polynomials of the Feynman parameters. And a new feature that we see in this form of the integral is illustrated now in this picture, where in addition to the roots of, for instance, the f polynomial being able to pinch the contour and give rise to singularities in that way, we can also have roots of this polynomial vanishing, or the vanishing locus of this f polynomial actually sitting on top of one of the integration endpoints of this integral, which happen where the Feynman parameters are set to 0. So otherwise, things are very similar. A version of the hierarchical principle also exists in Feynman parameter space, and it was recently proven by Marco Berghoff and Eric Panzer just a couple of years ago using a relative version of Picard-Lefschetz theory. And just as in momentum space, when we compute discontinuities in this representation, what will happen is we'll be able to represent those discontinuities as new integrals where the contour has been localized to some pinched surface, somewhere over here. And that will also in particular mean that we will start to forget about the integration boundaries at the origin of the Feynman parameter space, because our contour will be somewhere over here instead. And this is the observation that we're going to leverage in what follows. Let me first show some examples, though, of how these Feynman parameter integration boundaries are modified in a simple example. So this example was considered by Ruth Brito in a paper last year. It's just the triangle integral. And what I've drawn on the bottom here is 3 different integration contours that naturally arise in this example in Feynman parameter space. So this first plot over here is just the integration contour for the original integral, which is over positive values of alpha 1, 2, and 3. And this diagonal line here corresponds to the alpha 3 equals 0 surface, and that's why we're bound to this triangle. But once we start computing discontinuities of this integral, this integration contour gets modified. So for instance, if I compute a discontinuity with respect to one of the internal masses, m2, what happens is I end up with a contour that is bounded now by the alpha 1 equals 0 surface, the alpha 3 equals 0 surface, and the vanishing locus of the f polynomial. So this reflects the fact that this is a singularity in which the second Feynman parameter contour in alpha 2 was pinched, and therefore we forgot about the integration contour original endpoint at alpha 2 equals 0. Similarly, if we look at something like a threshold discontinuity, here where the momentum p squared coming in becomes the right value to create a particle of mass m2 and m3, we see that we end up with a contour that's now just bounded by a single Feynman parameter boundary, or one of the original Feynman parameter boundaries in f equals 0. And that corresponds to the fact that the other two Feynman parameter contours have been pinched by this singularity. So if we want to use this observation in practice, though, there are two questions that we need to address. So first, when we compute a kinematic discontinuity with respect to some singularity lambda, we need to have a way to decide which of these integration boundaries in the alpha variables have changed. And once we've decided which boundaries have been dropped, we need to have a reliable rule to rule out when a singularity on a different kinematic surface lambda prime can no longer be reached. Both of these questions are made difficult, again, by the fact that we don't, in general, have perfect knowledge of all the places in, for instance, Feynman parameter space or also loop momentum space where singularities arise. And that means that we can't reliably rule out, for instance, additional singularities once we've pinched some number of propagators. OK, so I'm going to spend the next few slides telling you how we address both of these difficulties. The first question we'll address by introducing what I'll call minimal cuts. And the second question will be solved by something we'll call the Euler characteristic test, which was due to these authors. I'll actually talk about the second one first. So the idea behind the Euler characteristic test is that singularities can only arise in Feynman integrals when the space on which the integration contour is defined degenerates. So specifically, I have this space in mind, where we start with a complex space of e-1 dimensions corresponding to our independent Feynman parameters. And we subtract out of this space the vanishing locus of the f and u polynomial and our original integration endpoints in the Feynman parameters. So the idea we should have in our mind is this picture again that I've been showing, where we can get singularities where some of the roots of, for instance, the f polynomial approach each other and sit on top of each other, or one of these roots approaches one of the integration endpoints sitting at alpha e equals 0. In those limits, something interesting topologically is happening to this space. So one way we can probe whether or not we have a pinch condition or an endpoint condition that's satisfied is we compute the Euler characteristic of this space, both before and after taking some kinematic limit. And if that Euler characteristic is the same, both before and after taking the limit, we know nothing interesting topologically is happening there, therefore there could be no singularity. So in practice, we can make use of the implementation of this test provided by Fevlo, Zera, and Tellin in the PLD code, where they use the fact that the absolute value of this Euler characteristic can be computed as the number of solutions to this system of equations for generic mu and nu. But so given what I've been telling you, there's a natural modification of this test, this Euler characteristic test, that we might consider. And that's because once we start computing discontinuities, if we start dropping some of these boundaries in the original Feynman parameter integral, well, it no longer makes sense to subtract off every single one. So we can now consider this modified space of integration variables where we only subtract off the integration boundaries that still actually exist in our integral. So this means we will be able to probe whether our integral can have a singularity on some kinematic surface, lambda equals 0, after we've dropped some of these boundaries in the original Feynman parameter space. And again, we can compute the Euler characteristic before and after taking some limit as we set lambda equal to 0. And the question is whether the Euler characteristic, or the absolute value of it, drops in this limit. If the numbers are equal, we conclude there can be no singularity and therefore no discontinuity that starts at lambda equals 0. So we can use this Euler characteristic test to reliably decide whether a given singularity can appear after we've dropped some number of Feynman parameter boundaries. But this still leaves the question of how we decide which of these boundaries we should think of dropping when we compute a discontinuity in the first place. So rather than determine which boundaries have actually been dropped, which is in general a hard question, it requires knowing where in Feynman parameter space all our singularities arise, our strategy will instead be to identify a minimum set of boundaries that must be dropped whenever we approach a given or take a discontinuity with respect to a given kinematic singularity. So we try and formalize this with what we call minimal cuts. So they're defined in this way. So given a Feynman integral I and a singular kinematic surface lambda, we refer to a set of cut propagators as minimal if the cut propagators partition the external momenta into the combinations that appear in the Mandelstam variables that appear in this description of the surface lambda. Also, each of the internal masses that appear in this polynomial lambda should appear in at least one of the cut propagators unless it's already appeared as one of the external variables. And third, one of these first two properties should no longer be satisfied if any of our cut propagators are taken off shell. So more intuitively, minimal cuts are supposed to make sure that all the kinematic variables that appear in lambda are just resolved by our cut diagram. So let me show you what that means in a couple of simple examples. So let's consider the triangle box integral, which has as a singularity this threshold where S12 equals 0. So the idea behind minimal cuts is we just want to make sure we cut enough propagators that when we contract all the uncut propagators, we end up with a diagram that can actually have the kinematic dependence we require, which in this case is P1 plus P2. So if we had not cut one of these three propagators, these two vertices would have been contracted into a single vertex, and we wouldn't have had the kinematic dependence we require. So we can continue to play this game, for instance, for a singularity that's a difference of Mandelstam variables. And we see here we've cut enough propagators to make sure that we depend or can have dependence on P1 plus P2 and P4 plus P5, because if we had not cut any of these four propagators, two of these vertices would have been contracted into each other, and we wouldn't have been able to resolve these variables. Okay. So we now have all the ingredients necessary to derive hierarchical constraints of practice. So let's say we want to investigate a given double discontinuity, whether it can be non-zero, something that looks like this. What we're going to do is the following. We'll first construct the minimal cut associated with the first discontinuity, which corresponds to a singularity at lambda equals 0. Once we've constructed that, we'll conclude that the Feynman parameter boundaries associated with each of those cut propagators can no longer appear in our integral because those contours have been pinched. And then we will compute the Euler characteristic for that modified space that I defined earlier, both before and after taking the limit where the second potential discontinuity surface lambda prime equals 0 exists. For instance, we can do this using a modified version of the PLD code. And if these two numbers are the same, we can conclude that this double discontinuity must vanish. In fact, nothing about this procedure requires me to take these two discontinuities in immediate succession, so we can conclude that this more general statement holds where I allow myself to take any sequence of discontinuities before these two. So let me just note one thing, which is that this method, we don't expect to give the full set of hierarchical constraints. And that's just because minimal cuts provide a conservative bound on what propagators / Feynman parameters have participated in a pinch singularity. And in particular, it remains possible that more of these boundaries have been dropped when we compute this discontinuity. But this is not a problem for us because this would, if we had this information, this would just make our predictions stronger. So we can be conservative and not worry about that for now. So we call the subset of hierarchical constraints that our method as I just described, allows us to describe genealogical constraints because they essentially describe what singularities or discontinuities can descend from certain preferred minimal cuts. In practice, anyway, we will see that these genealogical constraints account for the vast majority of possible hierarchical constraints in the two loops examples I'll show. So let me begin with a one loop example, just the two mass easy box. So this is an integral that depends on 4 Mandelstam variables and involves 10 singularities. And we can just run our method as just described, and we find 64 genealogical constraints of the form shown here. So for this lambda and lambda prime, one of these singularities shown in this diagram. And this is in fact so many constraints that it's easier just to show which singularities or sequences of discontinuities are allowed, and that's shown by these arrows here. So a few things to quickly note is that we can have at most one of the discontinuities in the first and the second line respectively appearing in a given term in our integral. And moreover, once we've computed a discontinuity with respect to something in the second line, we can no longer access any discontinuities represented by the singularities on the first line. And similarly, for the third line, we can't access anything above it. So this is actually a very restrictive set of conditions. And indeed, we can check that these constraints are obeyed to all orders in dimensional regularization. So let's now look at some two-loop examples. We can go back to this example of the triangle box. Running our new method, we find 156 genealogical constraints. And by checking against the known answer, we can see that we only miss 31 possible constraints in dimensional regularization. We can then consider something like this planar double box shown here. Now, a new subtlety arises because now in this case, since we don't have external momenta coming into every vertex, we don't have a unique minimal cut associated with every threshold. So for instance, I can isolate S15 by cutting here or through here, but that's fine. We can take that into account. And running our method, we find no fewer than 620 genealogical constraints where we miss only 25 more possible constraints by comparing to the answer. And then finally, we considered a non-planar double box example. Again, we have some subtleties that need to be thought about when determining minimal cuts because we have multiple ways we can represent the singularity surfaces of non-planar integrals just by rewriting them in terms of different Mandelstam variables. But again, we can take that into account. And here we find 540 possible genealogical constraints where we miss only 9. Let me highlight that these constraints actually follow from restrictions on both algebraic and logarithmic discontinuities, not just logarithmic ones. So we should also ask how constraining these genealogical constraints are in practice. So one way we can address this question is by building the space of functions we expect to contribute to one of these integrals. So I took the example of the double box shown here. So this integral is polylogarithmic and gives rise to 37 different symbol letters. And if we just build the space of wait for polylogarithmic symbols that could be constructed with these letters that also have appropriate first entries, we find 679 such functions. To give us some context, we can ask what the extended Steinman relations tell us about this space. So this is a set of restrictions that tell us that in this case S12 and S15 cannot appear next to each other in the symbol. So this set of constraints leaves only 569 possible symbols. However, if we impose our full new set of genealogical constraints, we can cut this space down much further to only 264 possible symbols. So we're actually finding constraints that are much stronger than what we knew to impose before. So let me just make one final point, which is that we can use this method to derive constraints on complicated integrals, even if we have minimal knowledge of the singularity structure of these integrals. So for instance, if we consider a complicated diagram like this that contributes to gluon fusion plus Higgs, or goes to Higgs plus jet, then if we just find some subset of the solutions to the Landau equations, we can start to impose or derive restrictions on these discontinuities, such as the one shown here. So there's really not a huge constraint coming from computational efficiency here. But I am running out of time, so let me now conclude. So we've presented a new practical method for deriving hierarchical constraints on Feynman integrals. And these genealogical constraints can be efficiently derived for integrals involving any configuration of massless or massless particles and hold to all orders in dimensional regularization. Of course, there's many future directions we might focus on in our work. So for instance, for now, we focus on scalar Feynman integrals, but it's also possible to include numerators and propagators that are raised to higher powers. It might be interesting to ask whether these types of predictions can help inform how we build bases of master integrals. And of course, finally, these predictions will be ideal for applying bootstrap methods to individual Feynman integrals, which we hope to do in the near future. So with that, let me just say thank you.
Okay, thank you very much for this very beautiful talk. So do we have any questions?
In some of the examples that you gave, you said that you were missing some of the constraints that other people have found. Do you have a picture of what constraints are you missing and why you're not seeing them through these discontinuities?
So we certainly understand why we miss them, and that's just because we're being very conservative in what Feynman parameter boundaries we drop, but no, we don't yet have a theory for why we're missing those specific ones.
Thank you.
Hi. So in the first three examples that you presented, you said that in the second and the third, there was some extra consideration you had to take into account.
Yeah.
So is there a bound on this like ad hoc consideration that you have to do for general diagrams, or just this?
Oh, sorry. Yeah,
only? Can you be more
no,
precise?
it's totally algorithmic. Yeah. It's something you need to think about, but it can be put on a computer. So there's not really an ambiguity in that sense, other than you just need to remember to sum over all possible minimal cuts.
Okay, thank you.
Yeah.
Hi. So at some point in your talk, you talked about forgetting the singularities that arise from the string of parameters at zero, at the boundary of integration. But in, for example, the differential equations method or like the PLD package, you also think about singularities that lie outside that region in general, right?
Yeah.
So are you not looking for these, or
Good.
to what extent does it actually matter, those singularities?
So nothing in this method relies on knowing the actual integration contour. The only thing we're using is the endpoints that we've cut out of our space using relative homology. So we know about that original endpoint at alpha equals 0, but we don't know about the actual integration contour. So we're getting every possible analytic continuation of these integrals. So in that sense, these constraints will definitely hold on any Riemann sheet without problem.
So it does pick up on...
It picks up everything outside the physical region as well.
All right, thank you very much.
Okay, well, maybe one last question from there.
Yeah, if you go back to look at the n=4 work that you did with Lance and other people earlier, these are now stronger constraints than the Steinman ones. Which other data can they replace?
So in the case of planar n=4, because we have dual conformal symmetry, we don't see these types of restrictions so easily because we've packed so many singularities into the same symbol letters. So empirically, I don't think we'll see much gain in those examples for that reason. So in fact, in that sense, this is better for things like the standard model where individual integrals will have a little more structure.
Okay, so let's thank again both Andrew and Ian